we want to calculate the density of a material, see if we can work out the density of a metal. And so we know that we can represent the metal in this small little chunk that's built by these little building blocks called the unit cell, all right, where the cube edge length is A. And we need to know the mass of the material inside that unit cell, and then the volume will just be A cubed. But where are the atoms positioned? And so what I'd like to do is I'd like to work out this theoretical density by looking through an example of the arrangement of atoms in aluminum. And aluminum actually has a particular arrangement of atoms. Well, maybe what I'll do actually is I will draw it for you first, and then we'll see that it's named with a descriptive name. So here's a cube, okay? Many elements actually have cubic symmetry to them, and aluminum is no exception to that. And we're going to position some atoms. And so it's cubic. What we're going to do is we're going to start by positioning atoms centered on the corners of this cube that I've drawn. Okay, I'll dot in the one in the back there. But that's not the whole story. There's not just ones on the corner. There's also ones centered on each of the faces of the cube. There's one on the top face there. And then its counterpart, or its opposite, across the other side of the cube, is that one on the bottom. I'll dash that in. Right side, left side, centered in the face, front side, and then the back. Okay, so those are the atom positions. These ones here on the face are positioned right in the middle of the face. These on the corners, again, the center of this sphere is centered on the corner of the cube. But we're actually only concerned about the portion of the atom that's inside the unit cell, not the entire atom. So we need to figure out what fraction of an atom is in each of those positions. So the face atoms, I'm going to try my best to draw here. Look at this. Okay, this is meant to be a. Look at this. I'm shading it. I'm trying to draw a sphere. We're modeling the atoms as if they're spheres. So if I took that atom there, I apologize, I'm a horrendous artist, and I sliced it here. So I'm drawing now a plane that slices through this atom. It would slice like this, and we'd end up with two hemispheres, right? There's my little catch light. And now does the other side look like this? This is all not my finest work. I apologize. But there you go. You get two. Let me label it so you know what you're looking at. Two halves. Okay. And we're only concerned, in fact, with the half that's inside the unit cell. The other half is part of the unit cell to the right. So that means at each face position, there's only one half of an atom. And what about the corners? Well, I won't torture you with my trying to draw a 1/8 of an atom, but there is in fact 1/8 of an atom at each corner. So what's the total number of atoms inside this cube, counting just the fractional portion of each atom that's inside the unit cell? Well, there's 8 corners to a cube, corners, times, we said 1/8 of an atom for each corner. So that gives us one complete atom. And then there's 6 faces, right, times 1/2 for each of those gives us 3. So the total, we say n equals 4, n being the number of atoms inside the FCC unit cell. Oh, whoops, I slipped up there. I told you the name, it's in the title, but face-centered cubic. This arrangement of atoms is called face-centered. It's descriptive, as I told you earlier. Why is it called face-centered? Because there's an atom centered right in the center of each face. Okay, so it's nice that way. It's descriptive, face-centered cubic. Okay, it also has another name. Sometimes it's called cubic close packed, but we're going to stick with face-centered cubic, or FCC, um, for our purposes, our discussion. Okay, so that's fantastic. We actually know that there's 4 atoms inside, so we're well on our way here to working out the density. So we'd say then, okay, the density is going to be equal to 4 times the mass of an aluminum atom, okay, and then divided by the volume of the unit cell. Okay, so we're almost there. Let's take a quick look at the units here, and then we'll generalize this for other materials, not just for aluminum. So we've got units there, number, the mass. If we're going to use assume that we're going to use the molar mass or the atomic weight, and that's what we pull off the periodic table. That's going to have units of mass units per mole, per massive number of atoms. And then the volume, well, the volume will be in volume units. So it doesn't quite work out yet. We have to account for the mole up there in the numerator. So we'll divide by Avogadro's number. And so we can actually just take this now. Now that we've done our little dimensional analysis, we've realized we need to add in Avogadro's number. And we can generalize and say that the theoretical density for a metal is going to be equal to the number of atoms in the unit cell times the atomic weight, or the molar mass, divided by the volume of the unit cell times Avogadro's number. And let me just label these for you. That's the atomic weight, as many people call it, or it's also commonly known as the molar mass. Molar mass. Okay, this is Avogadro's number. That's the volume of the unit cell. And that's the number of atoms in the unit cell. Okay, and that's an equation that's quite useful, so let's give that a red box, just for good measures. Okay.